and also for input and output. And so the question at hand is the scheduling of programs. So what happens is there is inside the machine, there is a timer circuit. This is a piece of hardware. And this timer circuit can be programmed to send a signal after a certain period of time, or periodically, based on a certain period of time. For example, every nanosecond, right? Or let's say every 10 milliseconds, there's a signal that comes to the CPU. It's connected to the CPU. The signal is called an interrupt signal. All right. When that signal occurs, the CPU will go to a section of memory which I'm going to put here as initials, as called an ISR. So that no matter where we are within the program, when this timer circuit asserts that signal, the CPU stops what it's doing and then goes to the code here in this ISR. The ISR stands for Interrupt Service Routine. Right, or a handler, an interrupt handler. The interrupt service routine will call the operating system scheduler. So in this code, we have a call to the OS scheduler. And the OS scheduler is keeping track of what programs have been loaded in memory, what program is currently running, how long it's been running, is it time for another program to run. And the OS scheduler will decide whether or not program 1 gets to continue to run, or whether we need to switch to run program 2. Yes. Yes. That's excellent. We're going to see there's going to be a cost when we switch from one to another. It's called a context switch, right? So when we switching from one program to another, and there is some cost associated with that, which we'll go into what's going on when that happens. Okay? It's sitting in memory.
So, like, say I'm sitting at the computer at something, right? I call for something else. What happens if, like, something to the ISR or something like that?
Okay. So as part of the lowest level code of the machine, the bring up, it's sometimes called the board support package, right? The lowest level program of the machine. It will set up a register in the CPU with the address of where the ISR will be for that interrupt. We can have multiple interrupts, and we can assign addresses to those interrupts, right? Right? This is the simplified version. No, trust me, this is the simplified version, right? So this is what's wonderful about this, though, is this is how the CPU, how the operating system can regain control of the CPU, right? The CPU is executing the instructions of the program, fetch, decode, store, fetch, execute, but in order to interrupt that machine cycle, there is literally a hardware interrupt that causes the CPU then execute this code that calls the operating system that gives it the CPU to run. And then the CPU keeps track of things, of all the statistics and whatnot, of all of the programs in memory. We still have that issue. We still have that issue, and we're going to solve that issue next. Yes, Jacob. Yes, it extends. All that's happening, Jacob, is that the OS scheduler has to consult more information when it's doing its scheduling. It has a list of processes. Okay. Yes, John. Yes. So, John, let's say that the machine has one program running. In fact, if we looked at our computers right now, all of our computers, we'd see that there's several programs running. Even if we have not launched anything from an icon, there are services that are running all the time, all right, that are taking turns with the CPU. So even with, let's say we had one program running on the machine, what would happen is the timer would fire. It would call the ISR. The ISR would call the operating system. The operating system would say, well, there's just one program loaded. Go back to doing it, right? So there's some amount of time that's taken up here. So to answer your question about switching between processes, there's a cost to handling interrupts, right? Because we have to go and we have to run some code. We'll figure out that cost. We don't have all the information yet to figure out the cost. Any other questions before we move on? So Nancy's point is, all right, well, what about that issue you mentioned where we've loaded up a register in the CPU that the program is depending on? What if the OS code modifies that register, right? When we go back to the program, will things work? And the answer is, unless we have a solution for that, we have a problem. There is a solution for that. And the solution for that is using a data structure, which you learn about in your data structures class, but it's actually implemented in hardware with the CPU. The CPU has this data structure. It's called a stack. A stack.